Welcome to this session. This session is part 2 of the Biochemistry, the Chemical Context of Life portion of the AP Biology newly redesigned curriculum. And I'm Renee McCormick with the National Math and Science Initiative, and I am extremely glad that you are here. So let's dive in and let's get started. We left off last time with a brief intro to covalent bonds, so I'm going to run through this fairly quickly because our main objective here is to understand how molecules begin to interact with each other, especially as they apply to biological systems. So a covalent bond is the sharing of a pair of valence electrons by two atoms. So if any of you have ever shared anything with, let's say, a sibling or another person of your age or of your household, you probably already know that sharing is rarely 100% even. So the same goes here. We're going to get some degrees of sharing, which makes bonds have a little bit more negative character to one end of them versus the other. And when we separate charge like that, where we have positive on one end and not so much positive on the other end, we talk about that as being polar. And we're setting up two different poles. All right, so in a covalent bond, the shared electrons count as part of each atom's valence shell. And you may have heard me say at the end of the last recording that confused me when I was your age. When I was in high school, I thought, how can you both count something? It seems like you're cheating somehow. And so my chemistry teacher helped me out with that, and he said, all right, if I ask your dad, how many kids are in your household? Well, the real answer is one, but it's not as exciting with one, so I'll make up a number. Let's say 3. He says, if I ask your dad how many kids he has, what's he going to say? 3. I said, okay, if I ask your mom how many kids she has, what's she going to say? 3. Are there 6 kids at your house? Do they count twice? It's like, oh, okay, I get it now. And that cleared up all my confusion. So if you've had that issue, I hope I just cleared yours up as well. So a covalent bond is formed between shared pairs of electrons. So we can have 1, 2, or 3 pairs shared. 4 pairs shared doesn't happen because that is going to be a whole bunch of electrons, 8 to be exact, all piled up between 2 atomic nuclei, and that's way too much repulsion. It's way too unstable. So what happens is that some elements can make more than one bond, and those elements are carbon, nitrogen, oxygen, phosphorus, and sulfur. Cenops. They're the only ones that can double bond. Notice fluorine and all the other halogens, chlorine, all that stuff is left out of this. Just cenops. And I remember this because I was forced to read the Odyssey in high school, and my favorite part of it was about the Cyclops, which is the monster with only one eye in its middle of its forehead. And so cenops sounds a little bit like Cyclops, and that always helped me remember it. So I'm going to stick with carbon since, all organic compounds for us are carbon-based. So if we had a shared pair of electrons between 2 carbon atoms, that would be pulling each one of these positive nuclei toward the center this way because opposites attract. And the positive nuclei is attracted to an electron, but it's even more attracted to a pair of electrons. So we write that as this, but you cannot forget that there are other possibilities going on with this carbon because all carbons make 4 bonds. So we call that particular pair of electrons a single covalent bond. So single covalent bond. But since carbon is part of cenops, it can make also a double bond. And I must point out that this bond is going to be shorter than a single bond. Think about why. That's what it looks like with that being a bond and that being a bond. That's 4 electrons in a fairly confined, close space, and these positive nuclei of these 2 carbons are finding them very attractive. And so they're going to move in even tighter to one another. So this bond is shorter and it's stronger. It will take more energy to overcome the attraction that 4 electrons have versus the attraction just 2 have in a single bond. I must also point out that the only other elements that any of cenops can bond with are also in, cenops. So I can't double bond with just any old thing. It's got to come from carbon, nitrogen, oxygen, phosphorus, or sulfur. We can also have triple bonds, and yep, you guessed it, they're the shortest of all. And by short, let me draw that a little differently. What I really mean is that not only is their bond length shorter, but the distance between the two carbons is a lot shorter as well. Yet, again, because there's 6 electrons piled up in there. So those two nuclei are finding that much, much, much more attractive, and they're being attracted to the clump of electrons more strongly when there's 6 of them than there would when there were 4, than there would when there were only 2. So, hydrogen, not part of CNOPS, but it's the simplest element that we have to play with, and so we like to start with it. So hydrogen has a single proton in its nucleus, and then it has an electron cloud. Note, there are no rings. If you listen to the first recording, you know that makes me happy. I don't like this idea of shells as a word, even though it's all through all biology books and some chemistry books. Most of the chemistry books have started talking about the electron cloud and not really using the word shell, or if they use it, they put it in parentheses. So my 2 hydrogen atoms sit here with their 2 positive nuclei, and of course each one of them randomly placed in that cloud has an electron somewhere. So as these 2 approach each other, energy perturbations, disturbances in the field if you will, actually occur, and we start to have some warping. So what you see now is that these electron cloud is being warped. As soon as you introduce this positive charge, this nice symmetrical cloud becomes distorted and warped. And you can bet that the electron is somewhere in this region for this to happen. And same song, second verse. This one, which had its nice symmetrical cloud, is also being warped. And its electron is occupying some region near here. Now, we talked about Goldilocks just a little bit in the last recording, that sometimes we get a little too excited about the 3 bears approach when in an experiment temperature is a variable and we have something, we design an experiment and we go, let's go with too hot, too cold, and just right. Well, here comes Goldilocks again, because these distances for a bond to occur can be too close, too far, and the bond forms when they're just right. And that has to do with energies and the offset of energies. So what we're looking at over here on this graph is potential energy, measured in kilojoules per mole. So as these 2 nuclei, these 2 atoms of hydrogen, first begin, so focus right here on step 1. As they begin, if they're this far apart, that may be so far apart they don't even know that the other exists, so they may not feel much attraction at all. As they move closer together, however, then this potential energy will start to change. As they move closer still, then we may actually have them close enough together they become known as one H2 molecule. If they get too close together, then they're going to repel right back out. And so what we see here are corresponding points along this graph. So this is a distance, not time. I realize that most of the graphs you've examined thus far in your life have time on the x-axis, but this is distance versus energy. So when they're far apart, we call that ground zero. So they're too far apart, they're getting closer, getting closer, getting closer, getting closer. Now they're really feeling that attraction for one another quite a bit, meaning the proton, and that's all there is in a hydrogen atom, is one of them. That proton is finding the electron over here, very attractive, and it's moving in tighter as a result of that, because opposites attract and likes repel. Same song, second verse. The proton over here is finding the electron over here, also very attractive, so it is also moving. If these move too close together, though, they will repel. So when they're at exactly the right distance, that's our Goldilocks moment, it's just right. The just right distance based on these energy exchanges, that's when we have bond formation. So energy's at a minimum, it's stable, therefore the bond forms. If they overlap too much, now we've got repulsion going on. Those 2 protons are getting way too close together and they're going to repel, and that's when we carry our journey on to over here. Now here is the biggest deal on this entire slide, and perhaps even in this entire presentation. Energy is released when bonds form. Otherwise, we wouldn't have a lot of bonded substances on the planet. And if I sat you down in a little contest and I said, quick, name 10 chemicals that you know of, you probably wouldn't name elements. You would name things like carbon dioxide and water and maybe glucose, sugar, something like that, because most of the things that you can actually name and that you can identify in your surroundings are bonded substances, because that's a lower energy state. Energy was released when each one of those bonds was formed. Energy has to be then absorbed when a bond breaks. This is why in cooking, for instance, we heat things, because we want to break bonds before we can make new ones. And so we have to add energy into the situation. So never ever forget, energy is released when bonds form, and energy is required to break bonds. All right, so to share or not to share? That is the question. The notation that we use to represent atoms and bonding is called a structural formula, and you've already seen me do it when I did this. Double bond, or single bond, double bond, triple bond. And that's a skeletal thing, because carbon makes 4 bonds. So if I add the rest of them, those bonds also want to be repelled as far apart in space as they can be. So if I write H2 structurally, I write that doesn't have any other electrons. 1 electron is here, 1 electron is here. So when you see something like a triple bond, you got to think these are electron pairs that are shared between 2 nuclei. And long, short. Obviously double bond somewhere in between. So we abbreviate these structural sort of formulas with H2. So we would abbreviate this as C2, and if let's say these were H's to keep it simple, then we would have ethane. No one's going to ask you that, just in case you already knew it. All right, and then we would drop to 4 H's, and then we would drop to, that's ethene if you care, and then this would be ethine. C2H2. So, just to, again, I'm certain that you know all this, and I'm certain I'm insulting your intelligence, and honestly, I kind of hope I am. Here we have H2. We can represent it this way, we can represent it this way, we can represent it with cute little cartoon-looking diagrams, which actually help us understand the three-dimensional shape better. But here is the region where the bond actually forms, that region of overlap between those 2 electron clouds. So for oxygen, it's right in here as well. So again, O2, note that oxygen is doubly bound, keeps it very stable, because you've got to overcome 2 different kinds of energies to break both of those bonds. And then our good buddy water. We have a whole PowerPoint coming up on water and why it behaves the way it does. But go ahead and embrace now that its geometric shape is bent. Very scientific word, bent. As opposed to the scientific shape name of methane, also another important gas in our early atmosphere and current atmosphere. So there are my 4 bonds. Notice the 4 regions of overlap right in through there, and there, and there, and there. Those are where my bonds form. But looking at this on the page, you think these are 90-degree angles, but you would be so wrong. You got to take it up off the page, and you got to let them expand into the 3rd dimension. That, think of it as like right now, this is like the x-axis and the y-axis. You got to get the z-axis action going in there. So when you have a methane, it has a 109.5 degree bond angle. Not that you care, but it's definitely not 90. So that's my point, is I don't want you to think it's 90. All right, so electronegativity is one of the things that help you when you're trying to discuss and explain these things on free response questions. I can usually ask a room full of AP Biology students at any point in the calendar year, what's the most electronegative element on the periodic table? And with a choral, wonderful, melodic, resounding fury, they answer fluorine. Fluorine is indeed the most electronegative element on the chart. Electronegativity decreases as we go down, and it decreases as we go across. And all of these numbers are there. If you want to pause and study them for a moment, you can see that. I ain't lying to you. But these things right up in here are the most electronegative, thus they are the most reactive, which is good news and bad news. As long as we want nitrogen in a place like an amino acid, want oxygen in a place like an amino acid, this is great. But chlorine and fluorine, yeah, not so much. Those wreak havoc in our body. We need some of those ions, but a lot of those ions give us grief and really can mess up a lot of our biomolecules. So electronegativity is simply an atom's, and be real careful with this vocabulary if you write about it, an atom's attraction for the electrons in a covalent bond. It's not a proton's attraction, it's the whole atom's attraction for just the electrons in a bond. Bond being the operative word. It's a bonding phenomenon. The more electronegative the atom, the more strongly it pulls it pulls the shared electrons toward itself. Now, not all sharing is created equal. That's why we have the electronegativity scale. And by the way, you may have heard it as the Pauling electronegativity scale. And yes, you can use that abbreviation for electronegativity because it's a lot of letters to write. Linus Pauling is my very favorite scientist because he is, at this point, I think I'm telling you the truth still. Might have happened in the last few years, but I think I'm current on this. That he's the only person to ever win 2 Nobel Prizes in 2 different fields. Other people have won 2 Nobel Prizes, but, you know, they're a one-trick pony and they got them only in chemistry or only in medicine. But Linus Pauling won the Nobel Prize for alpha helix and beta pleated sheets, which we'll discuss in a future Biochem PowerPoint very shortly. But so that's all about protein structure. But he also earned one in peace. So he got one in chemistry, even though it was biochemistry, and he got one in peace. You know, Einstein's little picture is all over the place. Linus is not such a cute guy, so his picture's not everywhere. But he really rocks, and so he's my favorite scientist. All right, in a nonpolar covalent bond, the electrons are shared equally. So that means electron, they're spending about the same amount of time around each of these nuclei in this bond, going back and forth. Now, obviously, they don't orbit around the nuclei. At least I hope that's obvious to you. They basically are just going back and forth, to and fro, to and fro. In a polar covalent bond, one atom is more electronegative. That means it's an electron hog. Don't write that, please. But think it. It's an electron hog. Oxygen has way more protons than hydrogen. Hydrogen has a single proton. So oxygen pulls the shared pair of electrons toward itself simply because it has more protons. It has more positive charge banked up in here, and so those electrons are being pulled. So this bond is now polar. The place it left is now slightly positive, and the place it's going to, which is this oxygen atom, is now slightly negative. So what is that thing? That thing is a Greek letter. You know this thing, perhaps, as delta, but what you might not know is that's uppercase delta in the Greek alphabet. This is delta as well, but you guessed it, it's lowercase. Sort of looks like a cross between a G and an S for us. So you can think of it looking like an S and think about it being slightly positive and slightly negative. So unequal sharing of electrons causes a partial positive or negative end for the whole molecule. Because of this shape, and here's what's missing, and this annoys me in a lot of these diagrams, there are more electrons here. There's 2 unshared pairs of electrons on oxygen. So now, because it has 4 valence electrons, it's got these here, and then it also has one here and one here. I said 4, I meant 6. Now it has 6 valence electrons. So now when we look at this, we see like an equator of sorts going through this molecule, with this end being negative and this end down here being slightly positive. So we can see a slightly positive here and a slightly positive over here. So this end is slightly positive. That's what makes water polar. In a nonpolar covalent bond, the atoms share the electrons equally. So in a polar covalent bond, we say there is a net dipole moment. That's the big people words for that. If you can't remember that, that's fine. Nobody is expecting you to know that. But if you've been a good chemistry student, you may have heard that before. If you're a AP chemistry student, you need to know this phrase. But it's not essential for the AP Bio exam. It is essential for the AP Chem exam, just in case you're in both classes. In a polar covalent bond, like I said, one atom is more electronegative. The atoms don't share electrons equally, and the unequal sharing causes this partial positive or negative charge for each atom. So here's my plus end, and here's my negative end. That's what I want you to walk away with. Now, in polar covalent bonds, again, one is more electronegative. They don't share equally. So we can get this in all sorts of different arrangements. So here I see negative, 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 and negative. There is no net dipole moment on this one because this molecule doesn't have a separate bonding area that's going to give it a positive charge. Now, if I replaced one of these chlorines with a hydrogen, oh, that's a whole new story. That sad little hydrogen electron is going to be spending more time toward that carbon nucleus, leaving a slight positive charge out here, Now I've got a dividing line of plus and negative on this molecule. But as long as all four things hanging off the carbon are the same, it's like a tug-of-war standoff. But if any one of these has a difference in electronegativity, then we're going to get some warping of that dipole moment, and we're going to start to set up the true plus end and negative end. So here's a question for you. Which of the following statements best describes the difference between an element and a molecule? I'm going to give you a moment. Pause me. Don't cheat. Pause me. Contemplate these answers. Nobody's watching. Okay? Contemplate those answers and see what you think. Welcome back. Now let's see what's the best description of the difference between an element and a molecule. An element is composed of only one kind of atom, that being the important part. Molecules can be composed of more than one kind of atom. So why are the other answers wrong? An element's composed of atoms, a molecule is not. That's the wrong part. A molecule is, so get rid of the not. Elements always have lower atomic weights than molecules. Nope. They have the combined atomic weight of its constituent parts. So if I have H2O, hydrogen, two of them, they weigh 1 each, plus oxygen, which weighs 16, and that makes a total of 18 grams per mole. So it's the sum of the constituent parts, 2 H's plus an O. Elements exist in nature only as parts of molecules. No, they're not parts of molecules. Elements just exist in nature as elements. All right, for a covalent bond to be polar, the two atoms that form the bond must have, pause me, don't cheat. I'm back. All right, what do we think? Different electronegativities. To be polar, we have to have that difference in that tug of war over the electrons, and that's what you can think about it as. Here's that shared pair of electrons. If this side is doing a better job on the tug of war than this side, then this side is going to be slightly negative, and this side is going to be, in an absence of negative, which we lovingly call positive. So similar electronegativities result in nonpolar bonds. It's almost like, again, a tug-of-war tie over the electrons, and they spend equal distance between the two parts, or equal time between the two parts. The same number of electrons versus different atomic weights don't give you enough information. You've got to know the electron structure of the atom on the outside to really figure that out. So ionic bonds, switching gears on you, covalent, all about sharing, and we've embraced the fact that not all sharing is equal. That's not newsflash for you. Again, if you've ever shared anything with another human being, you kind of already knew that. And sometimes you're a little bitter about it too. But ionic bonds is a case involving greed. This will appeal to some of you. The future megalomaniac in economics folks among you. All right, so atoms sometimes strip electrons from their bonding partner. That's known as stealing. Please don't write stealing. This is what I want you to think. An example is the transfer of an electron from sodium to chlorine. So sodium has this one lone valence electron very far away from its nucleus, and it's shielded by 2 electrons here and 2, 4, 6, 8 electrons in the S&P of the second sublevel. That's the first, that's the second. We're out into the third sublevel here. So it loses that electron. That electron goes away, and we have a sodium ion. Where does the electron go? It comes over here to complete the octet, which is probably a phrase you know from chemistry, so that we get 2, 4, 6, 8 electrons, and because chlorine originally had only 7, it was lacking 1 to make an octet, and so this becomes a negative. So now we have no sharing of electrons between them. We have downright theft. So chlorine stole the electron to become the chloride ion. Now, the truth is, this is a pure charge and this is a pure charge. No more of this slight stuff with the little baby delta signifying that. No, this is actual theft, and that's an actual electron that was stolen. So now we get into something that's called a Coulombic attraction. So for the benefit of any of you that have had any physics, Coulomb's law is the product of two charges divided by the distance between them squared. So you can call that D or you can call it R. Since these are elements and atoms, that we think of them as spheres, so we often see R squared. And so the force of attraction, which is that Coulombic force, we put a C on that often, is proportional to the product of the two charges and the distance between them. So as you can imagine, this is a +1 -1 situation, and a +2 -2 situation would be 4 times stronger if the R's are equivalent, almost approximately the same. So now we have a full out charged situation. None of that slight stuff anymore. So these aren't just polar, these are ionic, and they are very soluble in water. So a cation is a positively charged ion, and an anion is a negatively charged ion. Most of you have been polite, and you have memorized those simply because we asked you to. If you need to know why, the cation always migrates to the cathode in a battery, in a wet electrochemical cell, as we call it, which you would probably call a battery. Just most of the batteries in your life are dry, because the wet ones are really messy. And who needs that in their cell phone? So an anion is going to migrate to the anode. These may be words you've heard before. So this is a positive ion, and this is a negative ion. And I could always remember that because that T right there, if you write like a first grader, looks like a plus sign. An ionic bond is that attraction between the two, between an anion and a cation. And compounds formed by ionic bonds are called ionic compounds. Go figure. Or salts. Note the plurality of that word. The only salt in the world is not NaCl. It's not all alone. There are many, many more. I can put anything else with chloride, and I can put just about anything else with sodium and make a salt. I can substitute all kinds of different elements in and make salts. The idea is that salts are ionic. These substances also come from opposite ends of the periodic table. Sodium is sitting over here in group 1, and group 8 are those noble gases that don't do much reacting. But group 7 right here are the halogens. And so you could take any halogen and any 1A metal and make a nice little salt from that. You could also take any polyatomic ion, which you were probably tortured with in a chemistry class to memorize sulfate, nitrate, nitrite, that sort of thing. Those also make them. So this is our good buddy table salt, NaCl. So you can see that the chloride ions are the big green bits, and that the little yellow bits are the sodium ions. They lost a piece, so they're smaller, and the nucleus pulls the remaining part of the electron cloud in tighter. Chloride ions, negative ions in general, are always larger because you stuffed an extra negative charge in there, and the protons are now not having a fair game of this. They're outnumbered, and they can't hold on to that one extra negative charge as effectively as they could when it was one-on-one. I call it having like a zone defense versus a one-on-one defense. All right, so new question for you. Why are covalent bonds more prevalent among biological molecules than ionic bonds? Pause me. Contemplate. Lots to read on these answers. This is the way the real AP exam is now. Lots to read. Take your time. Come back to me in a minute. Welcome back. Why are covalent bonds more prevalent among biological molecules? Because biological conditions are often aqueous. That's your good buddy water. And the water would cause ionic bonds to dissociate. So I can't have a structural molecule that's going to like become a bone or something significant, a wing, whatever, and have it fall apart in water. The whole organism would fall apart in the rain. That would be disastrous. So there is our answer, but let's visit why the others are wrong. A is wrong, obviously. Ionic bonds only occur between metals and nonmetals and therefore aren't usually present in biological systems. That's not true. We can have ionic things that involve all sorts of combinations, but that's not why. You can have double covalent bonds but not double ionic bonds, so covalent bonds provide more variety consistent with the structural demands required in biological systems. Okay, I'm not mad at you if you chose B, because you'd think two bonds were better than one, but the deal is ionic attractions are Coulombic attractions. They're in a whole different category, and they are enormously stronger than any combination of even 3 covalent bonds. Ions only form under extreme conditions not compatible with the cell's environment. That's not true. Lots of ionic compounds are very, very stable. Salt, NaCl, the one you know and love, being one of them. So here's where the trouble starts. This is where things are going to get tricky. If you listen to nothing else, I need you to listen to this next section very, very, very carefully, because we're going to have some serious confusion if you're a good student. The better student you are, probably the more confused you're going to be about this, because you got two camps at universities that don't necessarily talk to one another and aren't even always in the same building at the university. So they don't even see each other most days. You got the chemistry people and you got the biology people, and this is the biochemistry unit. So they have to come together on some things. But this is a rift. This thing I'm about to explain to you is a rift between the biology and the chemistry textbooks. The biology book speaks right at the beginning, in the first 50 pages, about weak bonds, when what they really mean to say are intermolecular forces. The word bond has a very specific meaning in chemistry. Pair, well, it doesn't even have to be shared. Just a pair of electrons. Usually they're shared because we're usually talking about covalent bonds. What they really mean are intermolecular forces. Inter means between, like an interstate highway goes between states. I-30 runs from New York all the way down to the tip of Texas. I take that back. It goes across Texas east and west. Geography is not my thing. That's why I majored in science. All right, so intermolecular forces, which we call IMFs for short, are what these really should be called. They are forces of electrostatic attraction between molecules. Take a balloon, rub it in your hair on a fairly humid day. Now, stick the balloon to the wall, because it will stick to the water vapor that's coating the wall. It's kind of fun. On a dry day, cold day, it doesn't work so well. But on a hot, humid day, it works quite nicely. So this is not at all the same as sharing a pair of electrons within a molecule. IMFs are between molecules. So you have to read questions carefully. Intermolecular versus intramolecular. Between, within. Within are what we've been discussing. Covalent. Weak bonds. They're careful not to use the word covalent when they say weak bonds. So weak bonds is a synonym for intermolecular forces. Furthermore, the biology book often speaks of van der Waals forces. Okay, that's a gentleman's name. The gentleman who actually first started kind of explaining the difference to people between what these things were. But the true van der Waals forces is a collection of forces which lumps all of the different sorts of IMFs together. Older chemistry books spoke of van der Waals forces, but when they did so, they specifically meant London dispersion forces, which is a subset of van der Waals forces. I know you're wondering why the grown-ups in your life just cannot get along. I wonder that a lot too. So, what's the big deal? London dispersion forces. Every single molecule has these, since every molecule has moving valence electrons. So essentially the electrons are in constant motion around the nuclei of both of the partners in this bond, but they're not always evenly distributed. It's kind of like a traffic jam. So around a given nucleus, which I'm just going to signify with a positive sign, not meaning a single proton, in that electron cloud, you've got electrons all floating around out here. At some point on this particular atom, there may be a traffic jam where these electrons kind of end up more on one end of the molecule, making it slightly negative, leaving an absence of charge, of negative charge over here, which leaves that end slightly more positive. It's not, in other words, the sharing isn't equal again, but this time the sharing is the sharing of space around a nucleus. If the electrons pile up in one portion of the three-dimensional molecule, which doesn't look like an egg the way I drew it, then we get a temporary concentration of that negative charge. All right, so we talk about this as being a temporary dipole. Why is it temporary? Because those electrons are not staying put. They're going to move. But if they temporarily do this, they sort of exert peer pressure on the other molecules in their environment. So if I get this distortion with electrons sitting on this end becomes more negative. This end then is left to be more positive. So a temporary dipole has formed. They're supposed to be all nicely distributed because they're equally repelling each other. But they're also moving very, very quickly. So sometimes you get these little pileups. So the larger the molecule, the more likely this is to happen. This is huge. The larger the molecule, Think of it as the higher molecular weight. Think of it as it has the more pieces. Think of it any way you want to think of it. It's a larger molecule with more protons and more electrons. The more likely this is going to happen because the valence electrons, as they're layered onto a nucleus, get farther and farther out from the mother nucleus, so they are less tightly held by the plus-minus attractions. And what wasn't polar at all is now sort of polar. Now, as soon as you get something sort of polar and you bring another molecule into the vicinity, if another molecule approaches, it's going to flip around in space to align its positive slight end with this negative end, and all of a sudden you don't have a chemical bond, but you have an attractive force. An intermolecular attractive force, an IMF. So this is just kind of the dotted lines are representing these attractive forces. It's also happening in 3 dimensions, meaning it's happening above the computer screen and it's happening behind, if you've got your computer upright, this computer screen. Mine's laying in my lap because I use a tablet. All right, so look at the diagrams. What's going on here? See all these electrons piled up over here? That's a negative charge. No electrons over here. That's a positive charge, and voila, you have attraction. They've just flipped these around because this is all moving. So no electrons, that's my slight positive region. Lots of electrons, that's my slight negative region. Now the Q represents quantity of charge. You know, we scientists, we love our variables. I know sometimes you don't feel the love for them that we do. All right, so you can look at the rest of these pictures and you can see what's going on. Again, negative, electrons clumped, no electrons, positive. No electrons, negative, electrons clumped, positive. Now this sets off a chain reaction in surroundings because notice that we also have attractions going this way. So this negative is attracted to this positive as well. Now this is getting more tightly held. If you got 2 attractions connecting this and this, all of a sudden this whole clump of molecules moves in closer and tighter on the x-axis, on the y-axis, and yes indeed, on the z-axis. And now they're more tightly held. Ly, more tightly held. Therefore, more energy is needed to separate them. So it might liquefy, it might go to the solid state, but you're going to have to add a lot more thermal energy if you want to melt it or if you want to liquefy it. So when we talk about boiling points and changing state, often this is what we're talking about, a difference in the IMFs. So what's the big deal? Well, molecules that were not originally attracted to one another now find each other quite attractive. Thus, it's very confusing. Thus, more energy is required to separate them, like I just said. In other words, molecules become sticky. Note the quotes. I'd rather you not write it unless you're going to write it in quotes. They adhere to one another. Sticky, baby word. Adhere, big people word. Collectively, such interactions can be strong as between the molecules of a gecko's toe hairs. I'm sure you've been up close and personal with the gecko's foot and you've examined the fact that their toes have hair. But a gecko's toe hairs and the surface of a wall. He's not really defying gravity, and he's not really attracted to the wall. He's really attracted to the water vapor on the wall. Because water, as we've already talked about, is very polar. And so that's where the plus minus comes in. Brick, stone, siding, log cabin, not so polar. Water vapor clings to everything on this planet. That's what humidity is. And so it's really the fact that the sticky toe molecules are attracted to the water vapor on the wall. So now, just in case you run into these words, just in case you have already run into these words in a chemistry class somewhere along your journey, induced dipole is just another name for what we just described as a London dispersion force. Again, IMFs is a broad category. And so any molecule, because any molecule has electrons, any molecule exhibits these London dispersion forces. But if you ever see a question that talks about induced dipole, It's inducing that separation of charge of the plus minus end on the molecule. Inducing as in inducing labor from a pregnant woman to make her have her baby, whether she wants to or not, whether her body's ready or not. Or inducing behavior in others, often for your own amusement. I suspect some of you are guilty of that. Then a spontaneous traffic jam is going to make these electrons pile up on one end, like we've already discussed, making a slight negative end and a slight positive end. And we signify which end is positive by putting a plus sign at the end of the arrow. So when you draw the arrow, you put the plus end always on that stumpy end, and the arrowhead end, there's an implied negative direction there. All right. Then we can have dipole-induced dipole, meaning I can bring something in that is a real dipole, and this is where it can induce behavior in a neighboring molecule. So it can warp this nicely evenly distributed nonpolar electron cloud on this molecule, because if this is negative, then the electrons that were residing on this end of the molecule now move to that end. So electrons pile up here, leaving an absence of electrons over here. And they tried to do this with the shading, that there's more electrons in the darker blue area, the lighter blue area, leaving a slight positive charge. And then in this induced dipole business, the electronegativity difference has to be enough. So I can have this dipole with this big enough electronegativity difference to make this really happen. So there's two more, now the two, I should say, are more attracted to each other than they were before the induction occurred. So here we have a molecule of HCl, lovingly known as hydrochloric acid, unless it's in the gas phase. It's only an acid if it's in the aqueous, if it's dissolved in solution. Otherwise, it's hydrogen chloride gas. But, point being, poor little hydrogen with its sad little one proton. Chlorine has a bunch. Chlorine is very electronegative. It draws the electrons of the bond toward itself, leaving nothing but essentially a sad proton out here. So that is going to then cause the same chain reaction of events in the x direction, the y direction, and the z direction in the three-dimensional world. So, a special case of dipole-dipole intermolecular forces is what I'm trying to spit out. Forces is known as hydrogen bonding. If I could change anything in my discipline, chemistry or biology, I would change the name of this. I would not call it hydrogen bonding. It causes so much confusion. It's really not a bond between molecules or between atoms. It is a force, an intermolecular attractive force between molecules, not atoms. So a hydrogen bond is not the same as a bonded hydrogen. That's the first thing I have to get across to you, so I'm going to say it again. A hydrogen bond is not the same as a bonded hydrogen. We're not trying to be tricky. Somebody just unfortunately named it hydrogen bond and it stuck years ago, decades ago. So a hydrogen bond is not bonded hydrogens. These are bonded hydrogens. Okay, that's an H, and that's an H, and this is an O, and this is an electron pair. These are unshared pairs out here as well, because these molecules are never complete. The artist may not have done as well in chemistry as you are. And then here's the other hydrogen. Both of those are very positive. So there is a pole, a separation of charge, kind of bisecting this molecule into two halves, where this is the slightly negative part where these electron unshared pairs are, and this is the slightly positive part down here. I should put my slightly in there. This is a true bond, a covalent bond. This slightly positive, slightly negative is setting up the hydrogen bond part. So a bonded hydrogen is within a water molecule.